Now, I know last term we started discussing the derivative of trigonometric functions. We looked at differential of sine is cos and derivative of cos is negative sine. Just going to do a very quick example here of when instead of having sine of 1x or cos of 1x, you've got a larger angle now, 2x. So in this situation, this is a chain rule because the outside function is cosine and the inside function is 2x. So we're going to write that as y is equal to cos u, where u is equal to 2x. So y du is cos is negative sine, and then du dx is going to be 2. So differential of the original function is now going to be differential of the outside times by the differential of the inside. Take u out, put its value back in. Alright, so that's a very, very quick example of how this is done as a chain rule. The example we're about to look at, you need to be able to do from this to this in one step. So cos differentiates to be the negative sine. The inside part stays the same. Chain rule it always does. The inside function always remains unchanged, so the 2x stays as 2x. And then we multiply through by the differential of the inside function. So that's how to do that in a nutshell. Now, we're going to be looking at ones to do with vectors. So we're going to consider the vector, position vector R. Now, I'm going to do 3 types of questions with this one. Now, question number 1, we're going to show that the velocity is always perpendicular to the position. Show that velocity will always be perpendicular to the position. First of all, we need the velocity vector. So, velocity vector is going to be equal to, we know that differential of displacement gives us velocity, so differential of that. So, do it down here, a bit more room. We now have to differentiate this. So in the I component, cos will differentiate to be negative sine. The angle stays the same, so it's 2t. And then 2 5s are 10. So 5 cos 2t differentiates to negative sine 2t. So that's the component in the I direction. So there's my velocity vector. Now we want to show that they're perpendicular. You may remember from when we did vectors last year, vectors are perpendicular if their dot product is 0. So we want to do the velocity vector dot the position vector. Well, we just times corresponding positions together. We take the I components, times them together, and add that to the j components added together. So the I components added together are going to be, look at the numbers at the front, 5 times negative 10 is negative 50, cos 2t, sine 2t. To that, I now do the same with the j's. 5 tens are 50, sine 2t, cos 2t. Now, we can see here, this component and this component are identical. One's positive, one negative. They add to 0, so therefore we know velocity is always acting perpendicular to the position. So you'll have your xy axes. This particular function here will give me the position at any particular time t. So the velocity will be acting perpendicular to that. Alright, now, question number 2. We want to show that acceleration is always going to be parallel to position. Show that acceleration is going to be parallel to the position. Well, once again, we need the acceleration vector. So acceleration vector is equal to the velocity vector differentiated. Let's go through it again. We have our velocity vector here. Differentiate that, j direction. There's our acceleration vector. We need to show that it's parallel to the position vector. Vectors are parallel if that one's a scalar multiple of the other. So this is cos 2t plus sine 2t. This has got cos 2t plus sine 2t. That has a 5 at the front. This has a negative 20 at the front. Hey, if I factor negative 4 out of this, so in here, that's the position vector. So I now have negative 4 lots of the position vector. So therefore, they are parallel. One more example. Give me a moment to clean the board and I'll be right back with you. Now, here's our next example. Here's our original position vector. So what we want to do is we want to be able to graph that. The best way to do that is if we have it in Cartesian form, y is equal to mx plus c or whatever format it happens to take. How to convert this into Cartesian form? Well, we don't want our variable to be time, we want our variables to be x and y. So we're now going to rewrite r in the form of x in the I direction and y in the j direction. So therefore, x is equal to 5 cos 2t and y is equal to 5 sine 2t. In this, ones with trig, they're handled a specific way. Other questions you're going to come across won't have trig values here for I and j. You'll just have things like x equals 3t and y is equal to t squared plus 4. Rearrange it to make it read t equals for one of the equations and substitute them to the other. They'll get rid of t, you're just left with x and y. That's a tip for the early questions. But when you have these ones to deal with trig, the best way to deal with it is as follows. If we go x squared plus y squared, you'll end up with, now I'm just going to expand that out and begin recombining it. So now 5 squared is 25. Now I've expanded, I've factorised out to 25. What I have now, inside the brackets I have cos squared of an angle plus sine squared of an angle. We know that comes to 1, so I now have x squared plus y squared on the left-hand side is equal to 25 on the right-hand side. That's the equation of a circle, centre of the origin, radius 5 units. And so the position vector traces out those particular points. That's how to convert your position vector into a Cartesian equation. So good luck with all those examples. Oh, by the way, totally off topic, what would you call it if you had a rooster looking at a lettuce leaf? That's a chicken Caesar salad.